Okay, class, today we're going to talk about the paired samples t-test. So paired samples t-test, very, very practical test that we can use. This is when we have two sample means and we have a within subjects manipulation. Another name for this test is the dependent samples t-test. Kind of in contrast to the independent samples t-test, whereas the independent samples t-test, we have two completely separate groups. For a paired samples t-test, well, a lot of those scores are coming from the same people. Okay, so the samples are dependent on one another. Let's go and see when we use the paired samples t-test. Okay, so we use the paired samples t-test if we want to see if two scores from the same group of subjects are significantly different from one another. So maybe we do a longitudinal study and we have subjects at age 6 and age 7, and we want to see if there's a significant difference in the performance of whatever between those two. Maybe we just do a within subjects experimental design and we have people in the experimental group and then they go and perform in the control group. So same scores or same subjects, but we measure their dependent variable multiple times. We want to compare those dependent variables to one another to see if they are significantly different from one another. So we don't know the population means. We don't know the population variances of either of our groups. And we have a study in which we have a within subjects variable. So just like the independent samples t-test, we run into a problem. The problem is we don't know what the null distribution, the null sampling distribution is going to look like, okay? When we have a one sample z-test or one sample t-test, it's easy to draw what this sampling distribution is going to look like. We have the information. We have the population mean. We have the standard error of this distribution. The standard error, of course, will be the population standard deviation over the square root of n. And if we know that, it's easy to come up with where the cutoffs are, okay? That's what we've been doing so far. But like the independent samples t-test, we have a problem. We don't know the population mean. So we've got to estimate that. And we don't know what the sampling distribution is or the standard error is. So we've got to estimate that as well. All right, so how are we going to do this? Well, here's the problem that we're going to start with. Suppose we've got 5 professors, so these are going to be our 5 subjects. And they have rated 2 different general psychology textbooks on how well they cover the material using a Likert scale of 1 to 10. All right, so book 1, book 2, and we've got the 5 professors. Okay, and we know that both of these scores come from Professor 1 and so forth, going through all the 5 professors. Now, under the null hypothesis, if we were to take the book 1 score and subtract it from book 2, and there were truly no differences between book 1 and book 2, then what we would see is we would have ourselves a lovely sampling distribution when sampling n number of people that would be centered around what value? It'd be centered around 0, okay? So instead of conducting the sampling distribution, instead of testing just the raw values, we're going to be testing the difference scores, okay? We're going to take this value minus this value and write that as our difference scores, okay? Here are all of our difference scores. We're writing difference as D, all right? And our difference scores should be 0 under the null hypothesis, if there's truly no difference between the usefulness of these 2 psychology textbooks. So let us go and conduct ourselves the paired samples t-test. Well, here's the formula. Okay, formula is right here. T is equal to, I don't know why I'm writing, but oh well, D bar. This is the mean of the difference scores. So we're going to find the mean for that. Okay, and we're going to divide that. And let me simplify this. Well, I'm not going to simplify. I'm just going to write another formula for it. I'm going to do little s d. This is the standard deviation of the difference scores all over the square root of n. Okay, these two formulas are exactly the same thing. I've just written it in a slightly different way with the standard deviation of the different scores as opposed to the variance of the different scores. This formula is nothing new. In fact, it's the same formula that you've done again and again and again. All right, the mean difference score, I could write out a different way if I really wanted to. Okay, in fact, the mean difference score is equal to the mean under condition 1 minus the mean for condition 2. All right, so if we look at that, this just becomes ye old t-test. All right, nothing new there. Okay, the only thing that we need to be concerned with is that how do we find out what the standard deviation or what the variance is of these different scores? We're actually going to have to calculate those out. All right, so this is our formula. Let's go and do it. So we've got all of the different scores that I showed you earlier. We're going to add them all up, divide them by 5 to get the average difference score, and it's going to be negative 1.8. All right, I'm going to find the variance of the different scores. So I'm going to take every single score, subtract it from the mean, and then square it. All right, and then I'm going to divide it by n minus 1, which in this case is 4. So this is going to give me a difference score variance of 1.2. Going back to my formula, I take the mean difference score and I divide it by the square root of the variance of the different scores, which is 1.2, divided by n, which is 5. When I do this, I find a t-value of negative 3.63, 3.673, my apologies. All right, so that's how we would go about finding this. I mean, the only thing that changes here, instead of looking at regular scores, we have to calculate the different scores and then do it that way. But other than that, it's the exact same thing as a one sample t-test, all right? Nothing really too new here. That's the wonderful thing about these statistics. They all are derived from one another. All right, so what is Cohen's d? What's our effect size? Our effect size is the mean of the difference scores. Okay, I wrote that as m sub d, but earlier on I had it as d bar. All right, same thing, just different notation. And here we have the standard deviation of the different scores. And as I mentioned before, we can take d bar, the mean of the different scores. It's exactly the same as the mean of condition 1 minus the mean of condition 2. All right, so let's do that for us. I'm just going to take the square root of the variance, and I find that it's 1.095. Again, the average difference score is negative 1.8. And when I do that math, I get negative 1.64. That's a very large effect size. And as I mentioned before, the sign of Cohen's d just tells you the direction of the effect. And if you report your means, you don't necessarily need this to be negative or need this to be positive. The sign doesn't matter as long as you know the direction of the effect. So I could write this as positive 1.64 and it'd be perfectly fine. Okay, so if we look at every single test that we've done so far, all right, here are all of the different tests we've done so far, what the z's are equal to, what the t's are equal to. You'll notice a trend, all right? You'll notice this trend. It's always a mean minus another mean, okay? That's mean. I know I'm horrible at writing. All right, it's always a mean minus another mean. This is how big of a difference is there between our sample means or between our sample mean and our population mean, all right? Obviously, the bigger this is, the more likely we are to have an effect, okay, or statistically significant effect, okay? So the first thing that we have in the numerator is the mean difference, the difference between our means, all right? And the larger this is, the bigger our t or our z is going to be. And by bigger, I mean either more positive or more negative, depending on the effect. And in the denominator, we always have the same thing as well, all right? It might not appear that way when we look at all of these different iterations, but it's always the same thing. It's a standard error. Okay, in the denominator for every single one of these tests, we have the standard error. And what is the standard error? That is the standard deviation of a sampling distribution. All right, so there is a lot of consistency in all of these formulas. They're all derived from one another, sampling distribution. There we go. Okay, so let's continue on. Another way to calculate t, which is a little bit easier if we have the information. So calculating difference scores and doing that by hand takes a long time. Okay, it takes a decent amount of time. I could ask you a question in another way. Okay, equivalent to the formula that I showed you earlier is this computational formula. Remember, a computational formula is a formula that is used to compute t a whole lot quicker than the conceptual formula. So in this formula, we've got the same thing in the numerator, okay? The difference between the mean in condition 1 and the mean in condition 2. But in the denominator, we have something pretty extensive, all right? It is the standard error of condition 1 squared plus standard error of condition 2 squared, all right? And you could easily calculate what the standard error is. Okay, the standard error of the means is the standard deviation of that condition divided by the square root of n, all right? But then we get something fancy here. We've got 2 times r sub 1, 2, standard error of 1, standard error of 2. So what's this r thing, okay? R, when you see this, is the Pearson correlation coefficient. We'll talk about this a little bit later in this class, in fact, close towards the end. So it's a Pearson correlation. All right, you could be given that in a problem. This is just the amount of a linear relationship between two variables, okay? The sub numbers here, 1 and 2, that just indicates that it's the correlation between condition 1 and condition 2. It's just the general formula here. Don't forget the 2 here. So it's 2 times the correlation times the standard error of the first condition multiplied by the standard error of the second condition. All right, so let's do a couple examples of this. All right, a developmental psychologist wants to know how the effects of aging on memory, wants to know the effects of aging on memory development. She gives 10 children, all right, a memory recall when they're 5 years old and the same test when they're 6 years old. So what information do I need to write down? I know that it's 10 children, so n here is equal to 10. All right, I like problems like this because they have numbers in here that are kind of lures, right? 5 and 6 are not going to go into the calculations anywhere. They're just the 2 conditions, okay? 1 second. All right, so n is equal to 10. The 5 and the 6 we're not going to put in. The 5-year-olds have an average of 8 words with a variance of 4. So I'm going to write here that my mean for 5-year-olds sub 5 is equal to 8. And my standard, no, not my standard deviation, my variance of my 5-year-olds is equal to 4. And it looks like I could easily calculate what the standard deviation is. For the 6-year-olds, all right, the mean of condition 6 for the 6-year-olds is equal to 10 with a variance squared 6 is equal to 9. And the correlation between the two of them are, we'll do the correlation between condition 5, condition 6, 5, 6-year-olds is 0.7. All right, the first thing I'm going to do is I'm going to write all that down in my very, very janky handwriting. Okay, so I should be good to go for the next part. Is there a difference in the population means in the memory scores between 5-year-olds and 6-year-olds. So here, with the difference between 5-year-olds and 6-year-olds, if I'm looking for just a difference, I know that this is a two-tailed test. So let's go and do the 4 steps. All right. So the null hypothesis is that the two population means are equal to one another. This is a general formula. And if I really wanted to be specific, I could write it as mu of 5 for the 5-year-olds is equal to mu for the 6-year-olds. Okay, but what I've done here is perfectly fine. All right, and the alternative, of course, is the same thing, but does not equals. Alpha is equal to 0.05, and it's going to remain 0.05. We've got a paired samples t-test, two-tailed test because we're looking for a difference. The degrees of freedom for a paired samples t-test is equal to n, the total number of subjects that we have, minus 1. It's not the number of data points that we have minus 1, okay? Because if we have 10 subjects, we've got 20 data points because we're measuring everybody twice. But we're looking at the number of subjects minus 1, okay? It's the number of different scores that we have minus 1. So we have 10 subjects, 10 minus 1 equals 9, and I'm going to look up my critical t-value in my table and find that the critical t, or t-critical, is plus or minus 2.26. All right, now let's get busy with the math. Boom. Okay, the first thing that I need to do is find my standard error of the mean. So I calculate my standard deviations for both the 5-year-old condition and the 6-year-old condition. And I divide those by the square root of n, which is 10. So I've got both of my standard errors. I'm going to square them here. So if I square 0.634 or 0.632, I get 0.4. If I square 0.949, I get 0.9. Minus 2 times the correlation between the two conditions, which is 0.7, multiplied by the two standard errors. I'm going to do this expression. It ends up being 1.13. I have negative 2 over 1. Or the square root of 1.13. And when I finally calculate this out, I have negative 1.228. Since this is less than the critical value, I'm going to retain the null hypothesis. Does it matter which condition I call condition 1 and which one I call condition 2? Not really. Okay, it doesn't matter. I'm going to come to the same conclusion for the most part. I just need to be mindful when I have a one-tailed test that my means are going in the correct directions, and that I've written out my alternative hypothesis correctly. If I do that, I am completely good to go. So to find Cohen's d, we need the standard deviation of the different scores. I didn't give you any different scores for this problem, but I know that this expression in the denominator of my computational formula has to be equal to SD divided by the square root of n, and I want to get SD. So what I can do is I know that what's here in the denominator is equal to 1.06. I can just do a little bit of algebra and multiply both sides by the square root of 10. And when I get that, I get what the standard deviation of the different score is, which, as it turns out, is 3.352. So to get Cohen's d, I'm going to take 8 minus 10, the means of my two conditions, and divide it by the standard deviation of the different scores, which ends up being 3.352. So I have a Cohen's d of negative 0.597. All right. So let's have a step 4. So we're going to retain the null hypothesis that there is not a population mean difference in the words recalled between 5-year-olds, and I present the descriptive statistics, and 6-year-olds. And I present this descriptive statistics, t, in parentheses, the degrees of freedom, equals whatever the t-value is that I calculated. And p, since we retain the null hypothesis, we know that p has to be greater than 0.05. Okay. D, Cohen's d, is equal to negative 0.597. If I were to put this as positive, it would be perfectly fine. We would assume the direction of the effect because we know what the means are. Okay, let's do one more example here. So a psychologist, ooh, that's not good. Let me fix that when I upload these slides. A psychologist is interested in how people learn better in a crowded room or in a quiet room. 15 subjects studied a reading passage in both conditions. In the quiet room, subjects recalled 20 idea units with a variance of 10. In the crowded room, they recalled 15 idea units with a variance of 12. The correlation between the two scores was 0.5. So conduct the appropriate test to determine if the population mean of idea units recalled was higher. Ooh, was higher. What do I think of when I think of this? Okay, I think that I've got a one-tailed test. I think I'm going to have one of these in my alternative hypothesis. Okay, so let us go and solve the problem. So my alternative hypothesis is that my mu, my population mean of condition 1, which is going to be the quiet room, is greater than my population mean of condition 2, which is the crowded room. I could switch them, okay? I could have instead, okay, I could have the population mean of the crowded room and the population mean of the quiet room. But instead of having a greater than sign, I would have to have the less than sign. Either one of these is perfectly correct. It just depends on which mean you talk about first. Is it the quiet room or is it the crowded room? The sign of the alternative hypothesis is going to change depending on which one of those you write out. And whether or not your t-value or your critical t-value is positive or negative depends on this as well. So right now, as I have written this with we're predicting that the quiet room is going to be greater than the crowded room, I'm going to have a positive t-critical. All right. So let's state our decision criteria. Alpha is 0.05. Of course, we have a paired samples t-test. It's a one-tailed test. Our degrees of freedom is equal to 15. I think in the problem I mentioned that we had 15 subjects. 15 subjects. Yeah, there it is. So 15 minus 1 equals 14. And the critical t, or the t critical, is equal to positive 1.76. And I looked that up in my table. So now let's do some math. I am going to calculate my standard errors. I've got those here. All right. I'm going to have my t is equal to the mean of the first condition minus the mean of the second condition. In this case, it is the mean for the quiet room compared to the mean for the crowded room. And in the denominator, I'm going to have the square root of the standard error of the first condition squared plus the standard error of the second condition squared minus 2 times the correlation between the two scores multiplied by the standard errors in both of the conditions. Okay, so when I do this, I have 5 over the square root of 0.736, or 5 over 0.858. This is going to give me a t-value of 5.826. This is going to blow the critical value out of the water. Okay, beautiful. But we're not done with step 3. We need to calculate Cohen's d. So using the same formula that I showed you guys in the last problem, 20 minus 15, we have 5. We're going to multiply what's in the denominator by the square root of n. And when we finally do this, the effect size is 1.51. That's a pretty large effect. There's a standard deviation unit and a half difference between the two conditions. So the way that we would write this up, we reject the null in favor of the alternative that there is a population mean difference in the number of idea units recalled between studying in a quiet room and studying in a crowded room. And I give the descriptive statistics in both these conditions. T, with the degrees of freedom, is equal to 5.826. The p-value, since we're rejecting the null hypothesis, is less than 0.05. And Cohen's d is equal to 1.51. Okay, I hope that was helpful for you guys. Have a good day, and I will talk with you later. Thank you.